work, energy, and power. Okay. So this is the sixth chapter. Obviously, for us to understand this chapter, we need the basics of the previous chapters. Write it down. Chapter 6, work, energy, and power. Okay. So let's try to analyze how your syllabus is actually designed. See, the first chapter was physical world. I told you it gives you the introduction of all the branches of physics and all those things. The second chapter was units and measurements. Means you got an idea of what are all the units present for different physical quantities that are being measured. Right. So what about third chapter? It is motion in a straight line. So here we try to concentrate only on the motion of the object, which is moving in a straight line. We were not concerned about the cause of the object. Similarly, we studied about motion in a plane, right? That is two dimension. Then we saw what are the laws of motion. So if you observe what is the motto of all the topics present here, these three chapters are mainly concerned with respect to what? You see, what are these chapters concerned about? The name itself is suggesting, no? What is common in both, all the three? Why, why is no one speaking? What is common? Motion, and here also we are concerned about motion, right? But what is the difference between these two chapters and the last one?
The in laws motion, a straight line and plane, we look at just how the motion takes place. While
Yeah.
in lots of motion, we know its origin, how the motion is caused.
Yes, we saw what is the cause, right? Whereas in these two chapters, we were not concerned about the cause. So the reason why work, energy, and power is actually kept after the laws of motion chapter is because what did we mainly concentrate on laws of motion? We concentrated on a parameter called as force, because we mainly spoke only about Newton's law, nothing outside it. Right? Newton's laws in terms of different physical quantities. One is in terms of inertia, one was in terms of linear momentum, one was in terms of action reaction, but everything was the same, right? So what exactly does the force do? The force will actually try to put the object in motion, right? So I'm repeating it. Force will try or tend to put the object which was at rest into motion, or if there was already a motion, a uniform motion existing for the particle, it will try to stop it. I hope these 2 points are clear, right? That is the first law that I am speaking about, first law. And the magnitude of force that we applied is given by the expression m into a according to second law, right? But one point is clear here. The force is causing what? The force is causing or opposing what?
Motion.
That's right. So force is causing or opposing the motion. So if the whenever what do you mean by motion? Motion means the object has got displaced. Right? What if you look at the basic definition of motion? If the displacement of the object is changing with respect to time, then we say that the object is undergoing or is said to be in motion. Am I right? How it is so, that is a different aspect. How it is moving, it's a different question altogether. But what exactly happens in motion? The displacement will change with respect to time. So in this chapter, what we are going to concentrate upon is we will see the combination of the force that is being applied on an object and the displacement the object is experiencing in the direction of application of force. That is what is called as work. The capacity to do work is called energy, and power is defined as the rate of doing work. So now we are going to start with the term work. Okay. So this is a concept which you would have learned in your lower grades. So what do you mean by work? Actually, we cannot define what is work. We can only talk about when is work said to be done. Can you guys tell me?
When a force is applied and the object moves, we can call it as work, sir.
Okay. So that's right. But I want to make a small correction. See, listen. You have an object of mass m, right? So you're applying a force and the object is moving in this direction. Okay. Can I say work is done?
No, sir,
Reason?
because it is perpendicular, sir. So if the force and displacement are perpendicular, no work is done, sir. The object doesn't move.
But how do you know? But how do you know that force and displacement perpendicular to each other will do no work? I never gave you any formula, right? We didn't discuss any formula. But you use the exact statement saying that force and displacement are perpendicular, so work is not done. So what would be your point of justification for this?
Can we say force is acting in vertical direction when displacement is towards the horizontal? So J component and I component.
Okay, you're taking the J component and Y component. So you're trying to say the component of force in the horizontal direction is going to be how much? If F is like this angle is how much? 90.
90 degrees.
So what? So it will be F cos 90. Cos 90 is going to be 0. Is this what you're trying to say?
Yes, sir.
There's one way of understanding. Okay. So if this statement is there, then we can say yes, work is done when they are perpendicular to each other. But as of now, we don't know any formula, right? So we need to first understand, according to physics, what do you mean by work done? Okay. Now let's say I'll give you a scenario. Okay. Let's say I'm giving you a bucket of water. Let's say I'm giving you a bucket of water. You're holding it in your hand and you're walking in this direction. According to basic English, are you doing work or not?
Yes, sir.
But according to physics, are you doing work or not? Actually, you're doing some work, right? When you carry a bucket and try to walk, in fact, if you try to run, you'll sweat. Okay, your heartbeat is going to go up. It's going to get raised. So all these things are happening. It means you're actually doing work, but according to physics, you're not doing work because of the same perpendicularity concept. Then, what is the definition we need to think with respect to work? So we need to answer certain questions. No, according to physics, when can we say yes, there is work being done? If the work is being done, you're trying to speak about the work done by whom? These are all the questions that are running in mind, right? So, to the statement which was already told by one of the students, I would like to add a point. So, can you repeat it? Whatever you told. Who gave the statement?
Me, sir.
Bhavtain. Yeah. Can you repeat your statement? I'll make the correction. Whatever you told, you repeat it. Work
So
is
for
said to be
work,
done
sir, work
when
is said to
force
be
is
done
applied.
when applied and the object moves, displaces from one place to
Object moves.
another. Yes,
That's
sir.
right. But one point to be added is, okay, the one point to be added is work is said to be done on an object when a force is applied on the object and displacement is caused to the object. Please underline this word in the direction of application of force.
Okay, sir.
Okay. So please make a note. Everyone, write down the definition. This is the basic point you need to have in your mind. Write down the definition of work done. There is no definition for work as such. Okay. We can only say when is work done. Write it down, please. Work is said to be done. Work is said to be done by a force. Work is said to be done by a force when force is applied on the object. When force is applied on the object and It causes displacement to the object, and it causes displacement to the object in the direction of its application.
Sir,
In the direction of its application. Okay. Now let's try to visualize what exactly is happening. Okay. Let's say I've given you a block to which there is a string tied and you're trying to pull it. Okay. You're applying a force F at an angle theta with respect to the horizontal. I hope you're able to visualize this, right? So I have kept it on a smooth surface and the object has reached the other point in this way. So all the distances are generally measured from the center. Why it is so, you will learn it in the next chapter. But remember, in physics, generally all the distances, mostly with respect to the object's motion, are measured from the center. Right? Let's say there is a displacement of S that has caused. Now, we can give a mathematical expression for work done. I'm writing it. Listen. Mathematically, work done by force capital F is equal to, observe, this F can be resolved into two components. One is F cos theta and the second is F sin theta. Accepted. Now revisit the definition. What is the definition trying to say? Work is said to be done by the force provided force and displacement are in the same direction. In this scenario, the force that we applied is neither along x direction or y direction. It is at some random direction. It is making an inclination with respect to the x-axis. So what is a component of force which is responsible for the motion of the object in the horizontal direction?
F cos theta.
Yes. So work done by the force is given as F cos theta multiplied with S. So if at all you are able to define a parameter like F cos theta multiplied with displacement, then this particular expression is what is called as work done. See, wherever you are seeing the word work done, the first question you need to ask is work done by whom? In this case, work done by the external force capital F. Are you guys able to understand this? It is F cos theta into S, or we can write it as F S cos theta, F into S into cos theta. We know that F is a vector and displacement is a vector. So what product between the vectors is going to give you cos theta?
dot product.
Dot product. So you can write it as F vector dot S vector. These are the different ways in which we can write the expression, provided.
So what is this? Displacement, sir. So this is
Displacement, yes. Provided force applied on the object is constant. So what do you mean by constant force? Means its value is going to be constant with respect to time. Am I clear till this point?
Yes, sir.
Okay. Now, let me extend the discussion slightly. What is actually moved on the floor? Let's say the block has mass m associated with it. Now, what I'm going to do is, from the previous chapter's knowledge, I'm going to draw the free body diagram of it. Okay. If I draw a free body diagram, then mg is going to be in the downward direction. Normal force is like this, F is like this, theta is like this, F cos theta is like this, F sin theta is like this, and displacement is like this. Am I clear with this diagram?
Yes,
I hope that you know I drew it fast. Okay. Now tell me, how many forces are actually there on the system? System means something which is under observation. Here it is block. How many forces are actually acting on the block? So it's a simple question. No? The diagram itself is telling how many forces are you able to see. It is N, mg, and F. There are three external forces acting on the object. Right. Now I'm going to put the question. See now I hope you understood what is the definition of work done. So what are the important points you need to concentrate? You need to concentrate on the force which is causing the displacement in the direction of its application. Now I'm going to put a question like this. So I'm interested to calculate the work done by normal in this scenario. What is the answer?
Zero, sir.
What?
0,
That's
sir.
right. Work done by the normal is 0
Why, sir?
since it is perpendicular. Apply the formula, no? Fs cos theta. Work done is Fs cos theta. So when I talk about normal will be the force. Displacement is S. What is the angle between N and S?
90 degrees.
So cos 90 will be equal to 0. Are you able to understand now why it is 0? Similarly, you guys tell me, what is the work done by mg?
0, sir.
It is still 0 since it is again perpendicular. So what is the only force that is doing the work here?
F, sir.
So work done by F is how much?
Fs cos.
Dot S.
So please understand. So are you guys able to visualize how you are supposed to solve? So whenever you talk about work done, work cannot be done by all the forces acting on the system. Work can be done only by those forces which are responsible for the displacement of the object. Is it clear? It's a very simple point, but I've seen many students ignoring this point and they struggle in 12th standard also, because the concept of energy is very, very important in physics. It's not only with respect to your 11th and 12th, anywhere else you go. But energy, you need to understand, energy is nothing but another term for work done, according to me. So you need to have a clarity of work done. Am I clear till this point? Am I clear? I hope there are no doubts.
Yes, sir.
Okay. Then
Yes.
I'm going to proceed with the next topic. See. Now, what was the scenario I've taken? I've taken the scenario where the block is placed on whom? The block is placed on a smooth surface. Now, what will happen if the same block is placed on a rough surface? Let's try to analyze the scenario. Okay. So, if it is placed on a rough surface, the same force F is applied, mass theta, F cos theta, F sin theta, and let's say the displacement caused to the object is S. Right. Now, what is the other force I'm supposed to include?
Normal and mg.
Normal and mg. Is that all? Is that all? Given the word rough.
Sir.
But there will
Friction,
be
sir.
yes, there will be a frictional force that is acting in the backward direction. There is obviously going to be a kinetic friction. Am I right? There is going to be kinetic friction. Right. Now I am raising the same question. Work done by first one, F. What is the answer? So in this scenario, if you observe, which component of F is actually responsible for the motion of the object?
Cos theta.
So what will be the value for work done by F? See, there are two options. One, you should be able to understand what I'm speaking. If you're able to understand, I want a response from you. If you're not able to understand, you have to let me know so that I will change. I'll try to explain it in a simpler way. So which option is right? Are you able to understand?
Yes. You can explain.
You're able to understand, right? Then people have to speak.
No, sir. Can explain in a simple way, sir.
Which part?
The voice is feeble, sir.
My voice is feeble.
Yes, sir.
Is it for everyone?
It is better now,
Yes, a
sir.
bit, sir.
Oh, sir.
Now it is better, sir.
Okay. So work done by F means, I'm telling you, I'm concentrating only on one point. You need to look at the component of the force in the direction of displacement. So work done by force will be F cos theta into S. It is still the same thing. Second, work done by mg, that is the weight of the object, is equal to how much?
0, sir.
It is still a zero. Normal,
0, sir.
it is
Zero,
still
sir.
zero. Because it is the same scenario as the previous case, except the fact that there it was smooth surface, here it is a rough surface. That's it. So, what will be the fourth one? Work done by the
Work done by
frictional.
friction.
How much is it? So, remember the basic formula for force is work done is force into displacement into cos theta. So, if I say work done by frictional force, then in the place of force, what should I substitute?
Frictional force.
Frictional
Yes, that's it.
force.
So, Fk into this Fk is also acting for a displacement of S. But the important point here is cos of how much?
0.
0. So cos
No,
will be 1.
180.
it's 180 degrees because they both are in opposite direction. And moreover, frictional force is a resistive force. Resistive force will always do a negative work. So it is going to be Fk into S into cos 180 is minus 1. So answer will be minus Fk into S. Are you guys able to understand this?
Yes, sir.
Right?
Yes, sir.
By looking at this example, we can classify the work done into three parts. That is positive work, negative work, sorry, zero work, or negative work. So when can you say the work done by the force is positive? So should the force support the motion or oppose the motion?
Support.
Supporting force is also always going to do a positive work provided there is a displacement. When is the work done by the force going to be negative zero?
No displacement.
No displacement. Means it is not able to create the displacement in the direction of its application. Third, when is the work done by force said to be negative?
Sir, when the force is 0 means. Sir, the force is 0 means it is opposing or supporting, sir.
Force is zero means you cannot speak. There is no force at all. No work. See, for you to define work, you need to apply force. Okay, you can, because work done doesn't have any definition for it. Work done by a force is what is the definition. That is why if you see, I'm always writing as work done by. I'm never calling it as work. Okay, for you to define work, you need to apply a force. The next question is about how the force and the displacement are.
Okay, sir.
Okay. So when can you say the work done by a force is negative? When it's trying to oppose the motion. Okay, that is going to be resistive force. Now, certain important points to be related with respect to force are, see, try to understand this because next part I'm going to explain using calculus. That will be slightly tedious. So ensure you're clear with the idea of work done. Okay. So you're doing what kind of a product between between force and displacement?
Dot product.
Dot product.
So what is the other name for dot product?
Scalar product.
Why is it called scalar product?
Sir, because vectors of
The output will be, when you do the dot product, yes, when you do the dot product between two vectors, the output will be a scalar quantity. So it is going to be, it is also called a scalar product. Accepted?
Yes, sir.
Now tell me one thing, is work done a scalar quantity or a vector quantity?
scalar, sir.
It's a scalar quantity. It is a very, very important point to be kept in your mind. So work done is scalar. Accepted? So please make a note. Work done is scalar quantity. I've explained why it is so. What will be the SI unit of work? What will be the SI unit of work done?
Newton meter.
Yes. force is measured in Newton, displacement is measured in meter. Okay. So there are two physical quantities which have the same unit. One is work done, and there is another.
SI unit of work is joule only, sir.
1 minute. 1 minute. Wait, I'll explain. So there are two physical quantities which have the same unit, Newton meter. One is work done, and the second is called as torque, TORQUE, which we will learn in the next chapter. Okay. So in both the contexts, it is Newton meter, but in the case of work done, Newton meter is also called as joule. Okay. Am I clear about this? You will see this Newton meter somewhere else also. But if the Newton meter is appearing for any other quantity other than whom?
Work.
Any other quantity other than work done, you should not use joule. So joule is represented by the symbol capital J. Okay. Am I clear about this?
Yes, sir.
Yes, sir.
Okay. So I'm sorry, I'm filling the gaps. You please make a clear note of it. So I'm repeating it. SI unit of work done is Newton meter, and this Newton meter is called as joule only in the context of work done. Now the next question is CGS unit of work done. What is it? It is dyne centimeter. This
Centimeter.
dyne into centimeter is called as erg. 1 joule is 10 power 7 erg. You can derive it from the concept of units and dimensions. I'm leaving this to you. Okay. I hope it is clear till this point. These are all very, very important points, guys. Please make a note.
So what is the DRG, sir?
It's called erg.
Erg, sir.
Just like how you are calling Newton into meter as joule in the context of work done, dyne into centimeter in CGS unit is called as erg.
Sir,
We don't
one
use
joule is how much?
10 power
Earth
7. One
Yes.
joule is 10 power 7 erg. If you have a doubt, I'll explain it. 1 joule is Newton, 1 Newton into meter. 1 Newton is 10 power 5 dyne. 1 meter is 10 power 2 centimeter. 10 power 5 into 10 power 2 put together is 10 power 7 dyne centimeter. Got it? It is 10 power 7 erg. Yeah. See, mostly this erg is used in, it's not used in the case of mechanics at all, because it's a smaller quantity. Are you able to understand this, guys? Shall I move on to the next concept? Okay. So, write down this point. Work done by all forces. I can say total work done.
We can speak loudly.
Total work done by all the forces on the given system is equal to algebraic sum of all work done in the system. Work done by the forces in the system. I'm trying to say total work done by all the forces on the given system is equal to the algebraic sum of all the work done by the forces in the system. Or I can say all the work done by the individual forces in the system. You please make a note of it. Algebraic sum of all the work done by the individual forces in the system. Okay. Let me explain what is the meaning of this. See, in physics, whenever you are performing, wherever you see total means sum. Right? Total means sum. So total work done by whom? Total work done by all the forces on the given system is equal to, I'm using the word algebraic. What do we mean by algebraic actually?
Variables.
It is not, and I didn't use algebraic variables. Here the only variable is force, work done, sorry. Here the only variable is work done. It is not variable, you need to take proper sign into consideration. You need to use a plus or minus in the case. Algebraic sum of all the work done by the individual forces in the system. Let me apply this concept. Okay. For example, if I give you this kind of a scenario where a block is moved on a smooth surface, if I ask you what is the total work done, then according to the statement, what you are supposed to do is work total is equal to work done by normal plus work done by mg plus work done by f. So what is the work done by normal? 0 plus work done by mg is 0 plus what is the work done by force? F into s into constant. Are you able to understand this point? So the total work done on this block is only by this force. That is what we are trying to conclude. Is it clear? In the same context, if I ask you, what is the total work done in this scenario? It will be, tell me, work done by force F plus work done by mg plus work done by n plus work done by kinetic friction. What is the work done by force?
F is constant.
Plus 0 plus.
Minus. Okay.
So what is the mistake I need to correct?
Being negative.
So it is going to be negative. Now you understood why it is negative. Actually, it is plus of minus. That is how we need to remember. You're able to understand? Means what you're trying to say is it is a difference of f cos theta and fk that is causing the motion to the object. Is that clear, guys?
Yes, sir.
So these are all the formulae that you can apply when you're dealing with forces which are constant in nature. Okay. So I hope you understand what do you mean by constant forces. Now the next scenario that is going to exist is, what is the work done by variable forces? Okay. So what do we mean by variable is, when you apply a force on the object and this force is changing with respect to time. If this is happening, that kind of a force is said to be a variable force. Okay. Now listen.
Can I say again, sir?
If the force that you apply on the object is changing with respect to time, means between 0 to 1 second, if you apply 5 Newton force, between 1 to 2 seconds, you apply 10 Newton force. Between 2.1 seconds to 3 seconds, you apply a force of 4 Newton. So what is happening? With respect to time, the force is changing, right? So if I ask you a question, what is the work done by the force between 0 to 3 seconds, will you be able to apply the previous formula?
No, sir.
No, sir.
Reason being, you don't know whether you need to take 5 in the place of f, or whether you don't know whether you need to take 10, or you
Whether the angle will be equal, sir, in all three cases, or
it will not be. See, acceleration is equal means force is constant, no? Because f is equal to ma.
Yes,
This constant, product of both will be constant. So when you say force is variable, acceleration is also changing, means it is non-uniform acceleration. Okay. So here what will happen is, dw is written as f into dx. Okay.
The dw
Then
will differentiate work, sir.
dw means small amount of work done. Wherever you see this d, it means small work.
So then dx means
Dx is small displacement. We can take ds then, because I'm using display s for displacement. No? So work done will be equal to integral of f into dx, ds from S1 to S2, where S1 is the initial displacement, S2 is the final displacement. Don't worry about the formula. I'll tell you how to solve the problem. Make a note of it. You should know how to deal, that's it.
So I have a doubt.
Yeah, tell me.
For instantaneous acceleration, we say it's dv by dt, no sir?
1 minute.
D.
Instantaneous. Yes, dv by dt.
So
That's
can
right.
we say this is instantaneous work done?
How is it instantaneous work done? Which one? dw.
Yes.
dw you cannot call. See, instantaneous. Instant means what? Time. Instant noodles. What do you mean by that? You will get it within no time. 2-minute noodles. That's what they're saying. No. Instant coffee means it is going to happen instantly. So instant has something to do with time.
Here
Here,
time is not taken instantaneously.
so that is why you cannot call it as instantaneous work done.
Okay, sir.
You call it a small amount of work done for small amount of displacement.
Okay, sir.
Okay. Yeah. So when a question is given to you, see, this is all about work done. There is nothing much to discuss. But you need to know when to use which formula, because we have seen two formulas, right? One is Fs cos theta and another one is integral of S1 to S2 FTS. That's what I'm trying to say. Right? But you should have a clarity of when to apply that. Suppose, see, I'm taking questions like this. Force of 5 Newton is applied on an object which causes displacement of 4 meter in the direction of its application. Find work done by the force. Okay. Now see.
So can I show the first question, sir?
Wait. You can copy it. So, observe. Okay. So, what exactly is the difference between the first and the second question? You can read it out. I'll give you 2 minutes time. Just go through it.
The first one we gave the value of force, sir. Second one we gave acceleration, sir.
Where did I give acceleration?
Sorry, sir, I did it as 5 meters.
So first one you gave, second one you gave it in terms of displacement.
Okay. So, by looking at the question, what you need to understand is, if the force does not depend on displacement, 5 Newton, right? 5 is a number, that number is a constant. If the force that is given in the question is independent of displacement, then this kind of a force is called as constant force. Whereas, if the force is dependent on displacement, then it is called as variable force. Okay. So what we are going to do is look at the solution. What is the answer for the first one? Work done is equal to force into displacement into cos theta. That is a general formula because the force is constant here. What is the force value? 5 into displacement is 4 into cos of how much value, guys?
The force dependent on displacement is variable force, sir.
Yes.
0 degrees, sir.
It is 0
Zero.
degrees. How did you get that 0 degree? What is the
Since it's
keyword
in the
given?
direction.
Because
Same
of the direct, it is in the direction of its application. In the direction is 0 degrees. So it is going to be 20. How much? 22. I hope you guys understood. This is the final answer. Whereas in the second scenario, what is happening? Work done is equal to, since I have variable force, there is no other option. We need to introduce integral of f into ds from where to where? S1
1
to
to
S2. But S1 is 1 meter,
1.
S2 is 5 meter, F is 5 S square ds. So 5 into S cube divided by 3 between 1 to 5. So 5 into 5 cube is 125. 125 by 3 minus 1 by 3. So answer will be 5 into 124 divided by 3. That is 620 by 3 joule. If you observe, in both the cases, the displacement is the same, 4 meter. But why are we getting different answers?
Because it's a variable force in second.
Because of the variable force. When I say 5 S square, what is happening? So tell me one thing, about on a comparative basis, 20 and 620 by 3, which one is a bigger number?
620.
620 by 3.
Obviously 620 by 3 is a bigger number, right? So since it's a bigger number, can I conclude that the work done in the second case is more? Means work done by the variable force is more because what is happening to the force as you keep displacing?
Increase.
It's
It will increase.
It is increasing because at 1 meter, what would have happened? Force would have been 5 Newton. At 2 meter, force would have been 5 into, in the place of s, you are going to substitute 2. That will be 20 Newton. You're able to understand it is exponentially increasing. So as the force is going to increase, the amount of work done by that particular force is also going to increase. That is why when you do the integration, the final result is coming out to be a greater value compared to the previous scenario. Am I clear with this?
Yes, sir.
So write it down. I hope it is done. Done or not?
Yes, sir.
Okay. I'll give you another type
Done,
of
sir.
instance. Now see. See, this is one scenario. Let's say there is another problem given like this. Find work done when force applied and the force applied on the object is F vector is equal to I cap minus J cap plus K cap, and displacement cost it's minus I cap minus J cap plus K cap. Write it down. Find work done when force applied on the object is F vector is equal to I cap minus J cap plus K cap, and displacement cost is S vector is equal to minus I cap minus J cap plus K cap. So how to do? What is the formula for work done? F vector dot
S vector.
S vector. But when can you apply this? I told you. You can apply this F vector dot S vector only under one scenario. What is it?
The work done. Now,
That is what work done. No. That's not the thing.
Force is constant, sir.
angle is 0.
That's the point. That is the point I want to make. So when the force is constant, you need to apply. Okay. See, these are all very, very important points, guys. So here, looking at this expression, can you tell me whether the force is constant or variable? So look at I cap, J cap, and K caps coefficients. Are the coefficients constant or function of displacement?
Constants.
So they are constants means force is also a constant. Okay. So in that scenario, yes, I can apply this formula. So when you do that, you are going to get I cap minus J cap plus K cap dot minus I cap minus J cap plus K cap. Okay. So how to do the dot product between two vectors? You multiply their coefficients and add. So coefficient of I cap and minus I cap 1 into minus 1 plus coefficient of J cap in the first one is minus 1 and the second one is also minus 1 plus coefficient of K cap in the first part is 1, coefficient of K cap in the second part is also 1. So what do you get? Minus 1 plus 1 plus 1. Answer will be
1.
Are you able to understand? So work done by this particular force in a three-dimensional space to cause the displacement of this much value in the same three-dimensional space is given as 1 joule.
Sir, if the question is given in the form of I cap, J cap means whether it is constant, sir.
No, that is not the case. I'll give you another question where I'll give you a variable force.
No, sir, how to identify whether the force is
If you
constant?
see the next question, you will understand.
Okay, sir.
Okay, look at the fourth question. Find work done by force F vector is equal to S cube I cap minus 2S square J cap plus K cap between the points S is equal to 0 meter to S is equal to 1 meter. Mithun, tell me now, are you able to understand the difference between both the questions? So it has nothing to do with I cap, J cap, and K cap. What is it you need to concentrate on?
Coefficient.
Coefficient.
You need to concentrate on the coefficients. Okay. So if you observe, the fourth problem is actually similar to the second problem, except the fact that here the magnitude of the force is given, whereas here the vector form of the force is given. I hope you are able to understand this point. Yes or no?
Yes, sir.
So what you need to do in this kind of a scenario is observe the solution that I'm going to do. Let the displacement vector be given as, be considered as ds vector is equal to ds I cap plus ds j cap plus ds k cap. Okay, this is the one you have to assume for every problem. This is a standard thing. Okay, then dw will be equal to f vector dot ds vector. So if I do s vector dot ds vector, tell me what is that we are going to get. S cube I cap minus 2s square j cap plus k cap dot ds I cap plus ds j cap plus ds k cap. Correct? So it will be s cube ds minus 2s square ds plus ds. Is there any doubt till this point?
No, sir.
No, sir.
So what will be the total work done then? Variable force, obviously integration s cube ds minus 2s square ds plus ds. Between which 2 points? They have given it 0 meter
0
to
and
0 to 1. So what will the answer be? So whenever you have a difference or sum, you can do it for individual. S cube is s power 4 by 4 between 0 to 1 minus 2 into integral of s square s cube by 3 between 0 to 1 plus integral of 1 times ds is s between 0 to 1. So if you apply the limit, it will be 1 by 4 minus 0 by 4 plus 2 into 1 by 3 minus 0 by 3 plus 1 minus 0. So it will be 1 by 4 minus 2 by 3 plus 1. So what is the answer? LCM is 12. We'll have 3 minus 6, 6 of 4, 8. 3 minus 8 plus 12. So 12 minus 15 minus 8, 7 divided by 12. Is it clear? So you can expect any of the 4 models.
Sir, if they're giving us I cap, j cap means you have to use this work is equal to f vector dot s vector, sir.
Yes. Work done is by default a dot product. Is this clear?
yes, sir.
Yes,
So
sir.
this is all about work done. Nothing else is not only here, throughout physics, wherever you go, we have discussed the maximum possible with respect to work done.
Sir,
Okay? Yeah, tell me.
sir, can we do the first question as S1 and S2, sir, using the calculus, sir? The first question, a force of 5
First
Newton.
question. Here you need not use calculus at all. No?
Why, sir? First question, sir. First, a force of 5 Newton is applied on an object.
That's
This one
what.
is-
What's the force here? It's a constant. Constant force means no calculus.
Okay.
Only variable force, variable only you need to use calculus. That is what I'm trying to say.
Okay, sir.
And moreover, the question itself will give you a hint of when to use calculus because you will see the word between. Only for variable forces, you will have the concept of between. Whereas in the case of constant force, what they will do, they mostly give you the displacement. Okay, but that word between cannot be the exact keyword. What will be the hint if you look at the question? If the force is a constant value, if it is just a number, it is constant force. Whereas if it is a function of S, it is a variable force.
Okay, sir.
Okay. So that is all about work done. Okay. So these are the concepts for today. In tomorrow's class, we will start energy, and we will discuss about different important concepts related to energy, and then we'll obviously go to power. Okay, so revise this concept before tomorrow's class.
Yes, sir.
Okay, then I'll see you all tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah.